Hello again, Algebra 2 students. We are back in our absolute value syllabus, and we are going to be on lesson 5, which is going to be vertical stretch and compressions. So let's check that off and scroll down here to lesson 5, vertical stretch and compression. The vertical stretch of a graph measures the shrinking or stretching factor in the vertical direction, meaning up and down. So, for example, if a function increases 3 times as fast as its parent function, then it has a stretch of a factor of 3. Also of note, if a vertical compression has a stretch by a factor between 0 and 1, meaning a positive fraction,
then a vertical compression is present.
So let's go to an example. What I want to do, as always, when I start with examples, is I want to plot the parent function first. You guys don't always have to do this, but I like to do it to kind of show you what's happening, what's taking place. My parent function, 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Sketch my lines in, sketch my lines in. Now, I want to come over here. I got f of x equals 2 times the absolute value of x, and I want to plot a table. Input negative 2 for x, I get the absolute value of negative 2, which is 2, times 2, which is 4. If I input negative 1 for x, I get the absolute value of negative 1, which is 1, times 2, which is 2. If I input 0, I get the absolute value of 0, which is 0, times 2, which is 0. And if I input 1 into the x, I get the absolute value of 1, which is 1, times 2, which is 2. If I input 2 into the x, I get the absolute value of 2, which is 2, times 2, which is 4. So now I can take these points and come over here and plot. And at 0, 0, I'm still in the same spot. However, if I go to 1, I'm no longer at 1, I'm at 2. And if I go to 2, I'm no longer at 2, I'm at 4. And if I come this way and I plot, at negative 1, I'm no longer at 1, I'm at 2. And at negative 2, I'm no longer at 2, I'm at
4. Drawing in my graph will allow me to see and compare that
my origin point stayed the same. However, each one of my other points went up by a factor multiplied by 2. That tells me that I have a vertical stretch by a factor of 2 present, and in the equation we see that by the coefficient in front of the absolute value expression being 2. How we would describe this from the parent function is we would say it changed by a vertical stretch of a factor of 2. So this is how we understand a stretch by a factor of 2. Let's look at another example of vertical compression, which with a vertical compress, like we mentioned above, it's a positive fraction between 0 and 1. So we look here and we have a positive fraction in front of our absolute value of 1/6. So let's plot our parent function, which is always how we start. And we have 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2.
So let's sketch in our lines and have our parent function.
Let's fill out our table.
Now,
when we plug in 6 for x, we get the absolute value of 6, which is 6, multiplied by 1/6, which 1/6 times 6 is just 1. And then when we plug in 3 for x, we get the absolute value of 3, which is 3. We multiply 3 by 1/6, that gives us 3/6, which is actually 0.5 or 1/2. If we plug in 0 for x, we get the absolute value of 0, which is 0. We multiply that by 1/6, we get 0. We plug in negative 3 for x, we get the absolute value of negative 3, which is 3 times 1/6, which gives us 0.5 again. And then if we plug in negative 6 for x, we get the absolute value of negative 6, which is 6 times 1/6, which is just 1. And if we come over here and we plot our points, 0, 0 stays the same. And then at 3, we go up to 1/2, which is about right there. And at 6, we go up to number 1. And then if we go the other way, we go to negative 3, we go up again to about 1/2. And if we go to negative 6, we go up to 1. And if we draw our line, that's that side of the function. That's that side of the function. we can clearly see that the function has been flattened out from the parent function. Another way to understand that flattening out is that's what we call a compression, because it's squeezing it down. So to describe this, we could say that from the parent function it was crushed, squished, whatever adjective you would like to use to describe it, but the proper mathematical term is to say that it was compressed by a factor of 1/6.